All right, guys, today we're going to look at periodic table and differentiate between metals and nonmetals, looking at some of their properties, how they are, how they differ. I know this is kind of a little too early. We're not even Halloween yet, but what does he want for Christmas? Guys, metals, nonmetals, metalloids, those are the three main categories of all the elements. And if you guys look based on the color code, the light yellow are metals. You can see the vast majority of all elements are metals. Think from the center of the periodic table to the left. The only exception being hydrogen. You guys should know hydrogen is a nonmetal. That is, the nonmetals are here on the right with the exception of hydrogen. And then there are a few metalloids. Okay, and so they're differentiated based on their properties. Metals have certain properties, nonmetals have certain properties, and so we're going to bring that up. That's a little hard to see. We're going to show you a little bit clearer. So metals tend to form cations. You guys should know that, right? You guys right? They tend to lose electrons, and so the metals tend to be composite. Remember, we looked at an activity series for metals, and some lose electrons more readily than others. So you remember these are called the transition metals. We have the alkali metals and the alkaline earth metals. And then they were also mentioning the nonmetals, however, tend to form anions. Remember, they have higher electronegativities. They tend to attract electrons, acquire negative charges. Once again, you expect the halogens to acquire a -1 charge. The oxygen group, or also known as the chalcogen group, -2 charge, and then the nitrogen group, -3. Alkalis +1, alkaline earth +2. Remember, all has to do how many valence electrons they have and what the arrangement is like in the valence shell. So metals, here's some typical properties, guys. They tend to be lustrous. You guys, that's the fancy word for shiny. You guys, metals are shiny. Malleable. That means you can apply force. You can take a hammer to it, and it's going to it won't break, right? It'll bend. Ductile means you can pull it into a wire, and they're good conductors of heat, right? So a lot of these are properties that you guys would already know just from your own interaction with metals. Metals and nonmetals tend to be ionic. You guys remember, because the nonmetals tend to take electrons from the metal becomes a positive ion, nonmetal becomes a negative ion. What holds those together is the electrostatic attraction, that is the opposite charge attraction. Those are ionic compounds. When you think of an ionic compound, think like salt, NaCl, right? Metal oxides tend to be basic. So you guys, this is a metal oxide. Like, let's take calcium oxide. That's lime. You put it in water, all right? So you put it in water. What will happen is it'll combine with the water and actually form calcium hydroxide. And you guys remember, well, we went over this. We'll go over this. I don't want to get too much into it because I don't want to confuse the issue. But you guys, this is a what's called a strong base, so it will completely dissociate. And it'll form calcium ions, and you see these hydroxide ions. Remember, that's what makes it basic. So you guys, when you're looking at your periodic table, you guys remember that first column? Those are called the alkali metals. That should sound alkali. Another word for basic is alkaline. So alkali comes from the fact that those, when they're placed in water, tend to form these hydroxide ions, and then the same with the alkaline earth metals. Remember the second column? So you guys can see what we're saying here. So metal oxides tend to form these hydroxide ions when placed in water. Nonmetals, you guys see they're totally different properties. They're not shiny, they're dull. Think about this as like sulfur, and I think this might be showing, I don't know what that's showing, maybe just a colorless gas, oxygen gas. It's brittle, so if you apply force to it, it's going to break. And they tend to be poor conductors of heat. They tend to gain electrons in reactions with metals to acquire a noble gas configuration. You guys remember that? We were saying halogens tend to be acquire a -1 charge. By gaining 1 electron, they now have a filled outer shell like the noble gases. Nonmetals, substances containing only nonmetals are called molecular compounds, right? You guys, what are key molecular compounds like carbon dioxide, CO2, water, H2O, right? You guys see they're just hydrogens, carbons, oxygens combining together. We'd say they form molecules. Most nonmetal oxides are acidic. So like, what would be a nonmetal oxide? Well, think about a nonmetal like carbon. If it's an oxide, wouldn't that be a nonmetal oxide? Well, you think about it, when you put that in water, you guys will notice this if you guys leave water overnight for an extended period of time, it'll actually taste a little different. Not to mention all the microbes and stuff, so that's why you don't want to drink water that's been sitting around too much. But there'll actually be a reaction with the water, and it will actually form carbonic acid. You guys remember how you recognize it as an acid, has the hydrogen in front, so that it combines in such a way. So, it will partially dissociate into these H+ ions and then the bicarbonate ions. So you guys see why we say they're acidic, because it tends to form acids, and that's the case with non-metal oxides. Metalloids, you guys remember the few in between, like silicon, germanium? Those have characteristics that you can say in this case it can be shiny, but maybe it has other properties. Maybe it's not very electrically conductive, and so it kind of has properties like both. We call those metalloids. Okay, so they're saying this is shiny, but it's brittle and fairly poor conductor, like I said. She says, I'm sorry, I guess it would have been more considerate of me to keep my scissors to myself. Is that what you call like a totally old Karen? I don't know if I'd be cutting that dude's earphones. I think he'd be knocking me out. All right, alkali metals, you guys remember that's the far left. They tend to be soft. In fact, you guys remember maybe from last year, I had actually cut it with a knife, like sodium and lithium. So they're, you guys remember, look, they all have one valence electron, they all end S1. Some other properties, they tend to have low densities. If you notice, the densities are really low. In fact, some have, it's a metal and it actually has densities that are lower than water. You remember water is 1 gram per milliliter or centimeter cube. Some of these have lower densities than water. And then they have low melting points. So they're going to melt, they're going to, go from a solid to a liquid at a very low temperature. So those are just some general properties we see of alkali metals. And then what we should already know is they have extremely low ionization energies. Remember, that means it requires very little energy to lose that outer electron. That's what makes them so reactive. Remember, you can take any of these, you put in water, and it's going to be explosive. Some of you guys remember that reaction from last year. Yeah, and that's what it's saying. They're famously known to be very vigorously reactive. Alkali metals, except lithium, react with oxygen to form peroxides. So that's just a little something. So it says with the exception of lithium. So lithium, if you had lithium and you had oxygen, what's it going to form? It's going to form let's see. Yeah, that would be lithium. That would be your typical lithium oxide. You guys know why it's called an oxide, right? You guys look, this has a -2 oxidation number and this is +1, right? So that's your typical oxygen. But they're saying all the other ones, like let's say we had sodium, you guys remember this is the first column. When that combines with oxygen, it says they tend to form what are called peroxides. So here's a peroxide. Now if you look at the oxidation numbers, remember sodium is +1. So if that's the case, if I have 2 sodiums and I have 2 oxygens, what does oxygen have to be? That's a -1. That's what we call peroxides, when the oxidation state of oxygen is -1 instead of -2, just a little. You guys remember the peroxide you guys are most familiar with is hydrogen peroxide? You guys, right? That's what you can use to bleach your hair or actually use for mouthwash. You see the oxidation state of oxygen is -1 there. Those are called peroxides. And those tend to be unstable because you guys remember the oxidation state that oxygen prefers to be in is a -2. So you can imagine when you form peroxides, they tend to be unstable, and so they're going to tend to be more reactive than your more stable compounds, oxides. So alkali metals, you can do a flame test. You guys, we did this last year in the lab as well. I don't know if we'll do it when you guys come back, but like you can take lithium and it's going to be like a bright red, and then this one I believe is potassium. It's kind of like a peach, and then I can't remember the blue. Can't remember which one that would be. But either way, you get these bright colors when you burn alkali metals. In fact, guys, that's what I do when I go camping. I actually take some of these, I take some salts, like lithium salts and some copper salts, and then when we're going camping, right, everyone likes to sit around a campfire, right? And it actually is pretty cool when you can throw out that salt, and then the metal will actually get ionized and then put off some pretty cool colors in the campfire. Alkaline earth metals, remember that's the second column, so we did the alkali metals. You guys notice what's characteristic of these, what is responsible for the fact that they have similar chemical properties. They all have 2 valence electrons, okay? You'll notice here, they have higher densities and melting points than the alkali metals. They're still not that high, but it's higher than the alkali metals. Their ionization energies are still really low, meaning you guys remember, they lose those electrons really easily as well. They're just not as low as that of the alkali metals. So like, for example, you can take beryllium and magnesium. If you guys look in the periodic table, just to show you guys, magnesium's right here, alkali metal, or even calcium. I don't know if you guys know that. You take that, if you have pure magnesium, pure calcium, you put it in water, you'll probably see it bubbling as it's reacting with the water. Shows you how pretty reactive and why they're so reactive, because they have exceptionally low ionization energies like the alkali metals. Reactivity tends to increase as you go down the group. So as you go down, like for example, Magnesium, calcium, as I'm going down, it goes beryllium, magnesium, calcium. Calcium you would expect to be more reactive than magnesium. Then I keep going down, strontium would even be more reactive than calcium. You guys remember why that is? Because when you guys agree, as you go down, the atoms get bigger, outer electrons are further from the nucleus, and then you got more and more shells of electrons, and those outer electrons are held even looser than the ones above, and therefore that's what makes them so reactive, is they lose electrons so readily. So you would expect the reactivity to increase as you go down. All right, you guys, now we're looking at a few nonmetals. We're looking at oxygen, sulfur. These are all nonmetals. You guys should remember on the right side of the periodic table. And then they're talking about, certain metalloids. Some elements are just naturally radioactive, meaning they're so unstable in their natural state that they will actually decompose on their own and give off radioactive particles, which we're not going to really talk about nuclear chemistry, I think, this year at all. Oxygen. You guys, here's a new term for you guys. So you guys, just a little bit more here, not too much. We have what are called allotropes. Those are different states of the natural elements. So you guys would know when we think oxygen, it's O2. And you guys remember why we do O2? We know it's that because that's where it's more stable, you guys, right? Because oxygen has 6 valence electrons, and so you'd expect to form 2 bonds, and so it's going to form a double bond with another oxygen atom. So the oxygen we have, the oxygen we're breathing in, is O2, right? But oxygen can also exist in O3. You can have 3 oxygen atoms combined together. These are called different allotropes of oxygen. So it tends to take electrons from other elements. We know that that's what oxygen is. And that process is called oxidation, and it was named after the fact that oxygen is so electronegative, takes electrons from other things. We call that process oxidation. Here's an allotrope of sulfur. Sulfur, its preferred allotrope is S8. And you guys, you can see, if you look on a periodic table, you can see sulfur you would expect to form 2 bonds as well. So it's not surprising that it would be in this like ring structure. See how each sulfur atom is bound to another sulfur atom. So they're sharing those valence electrons with adjacent sulfur atoms. That would be an allotrope of sulfur. The halogens, you guys remember the second to last column? They all have 7 valence electrons. You remember they tend to gain electron in order to fill their outer shell. The halogens. They have large negative electron affinities or electronegativities. Remember, they have a strong attraction for electrons. They tend to oxidize other elements. You guys remember what does that term oxidize mean? Taking electrons from other elements. So most things when they come in contact with fluorine, chlorine, bromine are going to be oxidized. And they said they will form metal halides. So if you take sodium with fluorine, it's going to form sodium fluoride, right? You remember that ionic compound, we call that a metal halide, because it's a metal with a halogen. Right, and they're just giving you some different facts. Chlorine we tend to add to water as a disinfectant. Basically, it kind of kills bacteria, and I think it also inhibits maybe algal growth, algae, right? And that's what we use for our pools. Okay, noble gases, almost done here, guys. Noble gases, far right. It says astronomical ionization energies. What that means is it takes extreme amount of energy to remove electrons from the valence electrons from noble gases, and that's not surprising because you guys remember it's already in a stable state, very stable state. Those the outer shell is full, they're strongly attracted to the nucleus, therefore it's going to require a lot of energy to remove any valence electrons. And not only that, their electron affinities are positive. You guys remember most nonmetals, when they gain electrons, right, that's an exothermic process, meaning energy is given off, because they go from a less stable state to a more stable state when they gained electrons. However, the noble gases are different. They actually have positive electron affinities. That means it requires energy. You'd have to input energy to get a noble gas to acquire extra electrons, and you know why that is, because their outer shell is already full. They have very minimal to no attraction for extra electrons, because where would those extra electrons have to go? Wouldn't they have to go into an exterior empty shell, since the existing outer shell is already full? So they are relatively unreactive, and that explains why the noble gases weren't, most of them weren't even discovered until much later than all the other elements, because they didn't react with anything, so you wouldn't even know that they were present. And they're usually found as monatomic gases. Looking on the periodic table, just so you guys see, obviously you can't see it again, but you know where I'm looking. Helium, neon, argon, those are just going to be monatomic gases. They just exist as individual atoms, right? Unlike oxygen, you remember oxygen's O2, nitrogen's N2. These tend to just be single atoms once again, because they don't really need to react with anything, they don't have a tendency to react with anything because their outer shell is already full. However, you can form some compounds. I mean, there's always exceptions. And look, so xenon, you can, under the right conditions, you can get it to combine with fluorine. But these are just exceptions. Notice I didn't purplize it, so you don't have to put that in your notes. Even krypton, you can create a krypton fluoride. All right, guys, good stuff. We'll see you guys next time.